Happy New Year, guys. Hope you guys enjoyed the drone videos I posted just a few days ago. But let's get straight into the problem. Today we're going to be doing the 2017 February contest silver problem. Why did the cow cross the road? Number 2. In this problem, the cows are going to be crossing the roads, and there are n crosswalks in which the cows can use. Each of the crosswalks has a signal light, but some signal lights are broken, and our job is to find the minimum amount of signals that Farmer John needs to repair in order for there to exist some continuous block of at least k working signals. Without further ado, let's take a look at the sample input. In the sample input, we're given that n equals 10, which means that there are 10 crosswalks, and k equals 6, which means that we're trying to get a continuous block of 6 working signals, and also b equals 5, which means that there are 5 broken signals. So if we just look at the block from 3 to 8, we can see that in this block there is only one signal that is not working. If we fix this signal, we can get a continuous block of 6 working signals, giving us the answer of 1, meaning that we have to fix at least one signal. Now, there are a lot of ways we can solve this problem. The simplest way is to just try everything that we can. So we're going to first look at the interval from 1 to 6, and we're going to cycle through to see how many broken signals are in there. If they're broken, we're obviously going to fix them because we're only looking at the intervals 1 to 6. We only want to make that interval all green. So we see that we have 3, so we put our current result as 3. And then we go to 2 to 7, and we cycle through all of that again. Now we only see 2, so we can update our result to 2 because that takes less fixing to do. Then we're going to look at 3 to 8, and we see that we have only 1, and we're going to update it to 1. We're going to keep doing this until we reach the end. This solution would give us a complexity of O of n squared. It would technically be O of nk, but because k is as big as n, so we can just write it as O of n squared. And because n can go up to 10^5, the solution is going to be too slow for this problem. However, we can optimize this solution by using a technique called sliding window. Because we see that every time we move the interval, we move the window here, we're actually repeatedly counting the things inside the windows. So 2, 3, 4, 5, it includes it in this window, and it also includes it in the next window. Every time we cycle, we're essentially counting that twice, and that is the reason our algorithm is slow. Instead of counting everything, we can just count the left and the right and update our result accordingly. Here's what I mean. So for the first window, we see that we have 3 broken signals. We can cycle through all of that first. But if we move on to the second window, all we're doing is we're shifting the first window by 1. So all we care about is this element that gets thrown away and this element that gets added in. So all we're doing is we're throwing away element 1 and we're adding element 7. We don't have to cycle through all of these in the middle. So we see that element 1, the one that we're throwing away, is a broken signal. If we're throwing away a broken signal, we can subtract 1 from our current. So currently we have 3 broken signals. If we throw away 1, we have 2 broken signals. We're going to add 7. 7 is already a working signal, so that doesn't count as a broken signal, so we're going to do nothing. In this interval, we see that we have 2 broken signals. We can update the result accordingly. Then we move on to the next window, And we see we're just shifting it by 1. So all we care about this time is this 2 and also this 8. So we're throwing away this 2 and we're adding this 8. So by throwing away this 2, because it's a broken signal, we're throwing away a broken signal, we have to subtract the number of broken signals by 1. So we're going to get 1. And then the 8 that is added on, it's not a broken signal, so we're not going to add 1. So our final result for this window is going to be 1. We can update our result accordingly. Let's do one more. So right now, all we care about is this 3 and this 9. We're going to try to throw away the 3, and because the 3 is already a fixed signal, we're going to do nothing to our current count. We're going to try to add 9 now. Because the 9 is a broken signal, so we're adding a broken signal to our count. So we should add the count by 1. So this 1 becomes 2. And we're going to keep doing this until we reach the end. This would only take a complexity of O of n, which would be sufficient for this problem. Let's go take a look at the code for this problem. So first I'm going to read in n, k, and b. Then I'm going to create a vector of Boolean called signals. We're going to first set all of them to be true. And true just means it's a working signal, and false means it's a damaged signal. So I'm going to cycle b times every time I'm going to get the current index of the broken signal. We're going to subtract it by 1 because we're counting from 0 here. Then we're going to set the signals of the current to be false. So we're going to set the current index to be false because it's broken. Now we're going to create the initial window that we're going to use for our sliding window technique. So that's just going to be the window from index 0 to index k minus 1. And we're going to say our broken count is going to be currently 0, cycle n, cycle k times. We're going to say if the current signal is false, which means that it's broken, we're going to add 1 to the broken count. Now we're going to actually do the sliding window. We're going to set our result to be the broken from 0 to k minus 1 because that's all we have currently. Then we're going to cycle from 1 to n minus k. So every time we cycle, we are going to be discarding I minus 1 because it's the previous one. We're trying to discard that. We're just going to say if it's a broken signal, then we're going to minus 1 from broken. And if it's not, then we're going to do nothing. If the I plus k minus 1 signal, which is the element that we're trying to add, if it's broken, we're going to add 1 to broken. If it's not, we're going to do nothing. And then we have updated the broken variable. Now we're going to check it with result, and if it's smaller than the result, we're going to replace the result. That should be the end of our program. This problem is a great demonstration of the algorithm sliding window. Make sure to check that out on USACO.guide. And we can see how simple the code becomes when we actually use this technique. Hope you guys enjoyed the video, and I'll see you in the next USACO problem.